Good morning, good afternoon. This is Mr. Lowe. Um, First of all, just want to say that I hope everybody's doing well and all your family members are doing well, and that you're still practicing that social distancing and that you're hanging in there. I mean, this can be tough. So, just want to say that I've seen a lot of good work turned in up to this point. Still like to see some more work on some assignments. But for the most part, I'm really happy with the stuff that's been turned in. So keep up the good work. I will try to make today's video as short as possible. We have 3 theorems that we're going to talk about today. And I'll try to give an example of each one as well. So today we're going to start chapter 12. We're skipping 11, going right to 12. It's continuation of circles. And today's lesson is over tangents. And so I'm going to define what a tangent is, and there's 3 different theorems. Okay. So a tangent basically is a line that touches a circle one time only. That's it. One and only once. Okay. So I'm just going to draw one real quick here. So we have a line. We'll go ahead and call it line L. Doesn't matter. Where it touches the circle is called the point of tangency. Point of tangency. And so right there, we'll call this point A, I guess. So this right here is a point of tangency at A. And so that's the big part, is learning what a tangent is. So that's what it does. It just touches a circle once. And so theorem 12.1 states that if you have a tangent line to a circle, then it has to be perpendicular with the radius of that circle that meets it at that point of tangency. So if we've got this radius and it actually connects to A, then it must be perpendicular to it. So this right here must be a right angle. Remember, perpendicular is this symbol right here. I'm not sure if you can see that. Let me move it over. There it is. So we got the perpendicular symbol. Remember, it's like an upside down T. It means to form a right angle. Okay, so that's what the theorem says. So if you have a tangent, it must be perpendicular to the radius that meets it at its point of tangency, which is at A. Okay, so think of a wheel. If this were pavement on the road, and then the wheel right here, if you draw from the center of the wheel straight down to the road, then there you have it. That proves that the tire is only touching the road at one point. Okay, all right. So theorem 12.2 basically is just the converse of 12.1. So now we're going to say everything backwards. It's really, really easy. So this one says that if you've got a line, okay, and we'll call it again line L, then if the radius of a circle forms a right angle, aka perpendicular, to that line at that one point of intersection, then this must be a tangent. It's just saying everything backwards. It's really, really easy. Okay? So, if you understand this one, you know this one. It's just saying it backwards. This says, if it's a tangent, then it's perpendicular to with the radius. This one's saying that if a radius is perpendicular to a line at the point of tangency, then it must be a tangent. So there it is. That's the only difference. So let's look at 2 examples that demonstrate this. Then we'll do the last theorem last. But let's go ahead and practice this one very, very quickly. So if I have a, let's say I have a point, let's see, maybe I can try to use this right here. Here, I'll just draw a new one right here. So if I have a circle here, no big deal. All right. And I have a tangent line here. And I have another tangent line here. No big deal. Right? And then here's the center, which is kind of a crappy center, but we'll be okay, I guess. And then we'll draw a radius here. We'll draw a radius there. And let's say that this angle right here, the central angle, remember those from chapter 10? Let's say the central angle is 140 degrees. Let's solve for the measurement of this angle right here. We'll solve for x. So let's solve for that angle measurement formed by these 2 tangents. No big deal. So we'll just pick some letters. I guess we'll go ahead and just keep it in order. So we'll go A, B, C, and we'll call this circle D. No big deal. Okay. So let's find the measurement of angle ABC, or just simply angle B. We can get away with that. Okay, so I'm going to put that so you can see it a little bit better. Okay, and so if you notice that this is a quadrilateral, in fact, it looks like a kite, doesn't it? Right? But we know that the sum of all the angles in a quadrilateral have to add up to 360. So if that's the case, we already know 3 of the 4 angles. Where are they, Mr. Well, here they are. This is 140. So we're going to subtract 140. Isn't this going to be a 90-degree angle now? Because a tangent and a radius has to form a right angle. So if that's a right angle, here is a right angle. So 90 and 90 is 180. So if you subtract all of these angles, and then what's left over must be the last angle. So that's 320. So if you should do all that subtraction, it's 40 degrees. So x equals 40 degrees. I hope that makes a lot of sense. The other example that I want to go over with you is, let's say we have, here's the center of the circle, and let's say we draw a radius here, and we have a tangent here, and we'll draw another one from here to here, which is obviously not a tangent. Well, if this is truly a tangent, this will be, again, a right angle, no big deal. So if I tell you that the radius of this circle is 3, so we'll call this x here, we'll call this point y, and we'll call this z. Okay, so if the radius, which is xy, if this is 3, and I want to solve the distance from y to z, so let's try to solve the distance from y to z, okay, then I need one more bit of information here, and that is, what is the distance from this point on the circle? I guess we can call this W. If I say that WZ is only 2, just from here to here only, we can solve for YZ. And the reason why is because all the radii have to be the same. So if this is 3, that'll be 3. So the total length of XZ is just 3 plus 2, which is 5. So notice that we have our right triangle. So that means we're going to use the Pythagorean theorem. Yes, my favorite theorem of all time. So a squared plus b squared equals c squared. We'll call this the a. That's all right with everybody. So we'll say 3 times 3 is 9. We don't know this distance, right? That's our b, if you will. So we'll go b squared. And then this is the c, which is 5. So 5 times 5 is 25. Do y'all remember the triple? 3, 4, and 5. So we already know that b is going to be 4. So let's just get that out of the way. But this is the work. So then you do some algebra. You subtract the 9. And then, of course, you square root. And then there you have it. b is 4. So be prepared to use the Pythagorean theorem on the worksheet that I give you for your assignment. Okay, that's going to happen. Okay, so just have that ready to go in your mind. Okay, so the last theorem is not so bad. 12.3, it basically says that if you have two tangents coming together at a common endpoint somewhere outside the circle, so let's say this is a point of tangency here, and let's do one right here. And there it is. Hopefully I can get there. There we go. So we'll call this one, I don't know, M. We'll call this one N. We'll call this point where they come together, we'll call that point P. Then basically the theorem says that if you, again, I was repeating, the theorem says that if you have two tangents that come together at a common endpoint here, then the distance from that endpoint to each point of tangency is the same. In other words, MP, that segment, is going to be congruent to the segment PN. So they're the same. So if that distance is the same as that distance, they're congruent. Okay, so let's do an example of that. This one's the hardest one to draw of all and make it look realistic. So let me see if I can do this real quick. I'm going to have to focus here. You know how I am with my drawing skills. So we're going to go across here. And then we'll go across this. Notice the point of tangency is here. There's one right there. And we got to make one more here. This is the hard part, and to make it look good. But there we go. Not too bad. And there's one there. So let me go ahead and move this up so you can see a little bit better. So here we've got two tangents here and here. We've got two tangents here and here. And then we've got two tangents, of course, here and here. Okay? Here and here. So let me go ahead and label these. We'll call this A, B, and C. We'll call this one J, K, and L. So here's the problem. Let's say I want to go ahead and try to solve for the perimeter of this triangle. The whole triangle, the whole perimeter. We're going to add up all the sides. Well, let's throw some clues in here and let's try to do that really quick. So if the distance from J to A is 7, the distance from A to K is, let's say, 4, and let's say the distance from L to B is 5. So let's find the perimeter of this thing, of the whole triangle. Okay? Well, since JA and JC are tangents that come together at J, then the distance has to be the same. So if that's 7, this better be 7. The distance from K to A is 4, so from K to B will also be 4. And the distance from L to B is 5, so from L to C will also be 5. Now all you got to do is add them all together. No big deal. So we got basically 14 plus 10 is 24 plus another 8 is 32. Any questions on that? So the perimeter is 32. So I'm just double checking here. 10, 18, and 14. 10 and 8 is 18, and 14 makes 32. All right. I hope this helps. You should expect the worksheet on Monday with the assignments on it. And anyway, good luck. If you have any questions, email me, and I'll do the best I can to help. Thanks.